Okay, so our next task, we've done convergence of sequences. Our next task is to do addition, multiplication, and series in the extended real line. And I'm going to focus entirely on the non-negative extended real numbers here. So we already know how to add and multiply numbers in the real line. And we'll use that. We'll base on, as usual, we're going to extend what we already know from the real line to work with the extended half real line, if you like. And I'll just explain what the operations are going to be. And the interesting thing is that there's at least one bit which is not obvious, and we're going to see what the problem is. Okay, so first of all, addition is easy. If you add infinity, and remember infinity is really the same as plus infinity for us. And if you add infinity to anything, infinity wins. There's a problem in the extended real line with addition. If you're not allowed to add plus infinity to minus infinity. That gives terrible problems and it's not allowed. You can't say, well, add infinity to minus infinity and get 0, because the associative law gets lost. I'll leave that to you to think about, but since we're going to work with the non-negative ones anyway, it's not an issue for us. But it's a similar problem if you want to do subtraction. You're not allowed to subtract infinity from infinity. You can't subtract plus infinity from plus infinity, or you will lose all the decent behaviour of addition and subtraction. You won't get any sort of sensible associative behaviour at all. So we'll never subtract infinity from infinity. If you ever write down something which has got subtracting y from x in it, and you don't know that x and y are both, you don't know that at least one of them is finite, then you know you've written something wrong, because your expression might not be valid. You're not allowed to assume that you can subtract things unless you know that at least one of them is finite. Okay, but otherwise, life is easy. Add anything to infinity either way round and you get infinity. Infinity swallows everything, but of course we use the usual addition if you're just working with real numbers in not infinity, so we already know how to add those together. So all that happens is, if you're adding two things together, if they're both real numbers, you do the usual addition. If one of them is infinity, then you end up in infinity. Infinity swallows everything. So here's a easy little exercise, but still, a bit of case-by-case analysis. Check, starting from the fact that you know this works in the real line, check that you've got commutative and associative addition in the extended real line. Well, okay, the extended half real line, if you like, the non-negative extended real numbers. That's a relatively easy exercise. The next one that you're going to see in a minute is much harder, especially if you're not efficient. This one you can get away without being that efficient, because there's not that many cases to worry about. The number of cases you have to worry about grows in the next one. What's the problem with addition? And what's the problem with cancellation? Well, 1 plus infinity equals 2 plus infinity equals infinity, but 1 is not equal to 2. Okay? So we've lost the cancellation law. It's the price you pay for introducing arithmetic with infinity. Cancellation law is still valid if you know the thing you want to cancel is finite. So x plus c equals y plus c implies x equals y is valid if c is finite. So we do have a little bit of the cancellation law left. That's basically the old cancellation law plus a special case where x and y might both be infinity. If c is finite and x is infinity, then y has to be infinity as well. So it does work still. But now we want to extend multiplication and we hit a problem. Why is that? Well, I've already warned you about infinity and adding it to minus infinity and how you don't know what you should say the result should be. And that one is abandoned and no good solutions found, and it's just declared that no one should ever try to add plus infinity to minus infinity. But it's different with multiplication. Multiplication, there was a new problem where you have to decide what happens when you multiply infinity by naught. And obviously, you can't just work it out from first principles, what infinity times naught should be. So what you have to do is look at what different theories you end up with if you try different values for infinity times naught, and which one are we going to introduce so that we've got some set of operations we're going to work with. And the standard one the mathematicians use, and which works best when you're trying to integrate. Well, let's think about this. Suppose you want to integrate over the whole real line the constant function naught. So suppose you want to integrate between minus infinity and infinity, naught dx. Well, however you go about it, you want to get naught. So naught should win. You're integrating over an infinite interval, an interval of infinite length, the constant function naught. You want naught to win. So we insist, in order to fit nicely with our integration and measure theory and everything, we're going to say that naught times infinity is naught. And that also turns out to give you a very good set of rules for arithmetic. So here's our multiplication in naught infinity. Naught wins in multiplication. Naught times infinity and infinity times naught are both naught. If you're not naught, then infinity wins in multiplication. So that's the next one. As long as x isn't naught, if it's some strictly positive extended real number, perhaps a real number, but possibly could be infinity as well. This includes the case of infinity times infinity. This time infinity wins. So infinity wins for multiplication as long as it's not being multiplied by naught. I'm not telling you what happens if you multiply by negative numbers, but you can guess that minus 1 times infinity will be minus infinity, and you'd be right. That's how you get, if you want to work with extended real numbers, you can still multiply. And of course, minus infinity times naught is still naught, and it all works out very nicely. And of course, if you're a real number, multiply by a real number, you do what you did before. So all we're doing is extending our usual notion of multiplication, and we just have to cope with multiplication by infinity. And multiplication by infinity gives you two possible answers here. Multiplication naught times infinity is naught. Anything else, anything positive times infinity will be infinity. And this case-by-case analysis is a bit harder. Especially hard if you introduce minus infinity as well and check that everything works when it can work, as long as you're not adding infinity to minus infinity. It's still true if you introduce minus infinity that the associative and distributive laws work as long as nothing in any of the expressions involves adding infinity to minus infinity. Slightly easier then to restrict to the non-negative extended real numbers. Slightly fewer cases to deal with, but you can still do it as efficiently as possible if you're going to check this. Or you can just take my word for it, that the associative and distributive laws work for addition and multiplication in the non-negative extended real numbers. Now, multiplication, we're used to having problems with cancellation, right? 0 times 1 equals 0 times 2 equals 0, but 1 is not equal to 2. We already had that, but now we've got the same thing with infinity. Infinity times 1 equals infinity times 2 equals infinity, but 1 not equal to 2. So we've got a new failure of the cancellation law for multiplication. But since we're already used to worrying, you now need to, when you do your when you're worrying about division by 0, you now also have to worry about division by infinity. Okay? Actually, we never will divide by infinity. Though one could talk about dividing a real number by infinity and getting naught if you wanted to. But I never intend to divide by infinity in this module. Okay, and now you want sum of the series. Well, of course, you want to have finite sums, we know how to add two things now. So you can add 3. And because everything's associative, it's unambiguous. So we can look at x1 plus x2, x1 plus x2 plus x3. You can look at x1 plus x2 plus all the way up to plus xn. And we can give that the usual sum notation. That's the sum from k equals 1 to n of xk. So we can do our usual notation with finite sums. And I've told you that the addition is associative, so you can add them up and a commutative. You can add them up in whichever order you like, you're going to get the same answer. So now if you want to do series, you do exactly what you did before. And you have to define partial sums. And as before, everything is much nicer than it used to be in the real line, because you don't have to ask, does this series converge or not? Because every series of non-negative extended real numbers can be summed to give a non-negative extended real number, which could be plus infinity. So you go through the usual partial sums procedure. You've got these xn's and you look at the partial sums, right? When you sum from k to 1 to n. And the idea is what happens to the partial sums as little n gets bigger. And you see, do the partial sums converge to something in the extended real line? But they have to, because you're adding on these non-negative extended real numbers, so they keep getting bigger. So you get S1 less equal to S2 and so on. Oh, and naught, of course, is less equal to 2. But this is a monotone sequence, monotone increasing or non-decreasing sequence of extended real numbers. So it has to converge to an extended real number. Moreover, they're all greater to naught. The limit has to be greater than naught as well. So these converge to another non-negative extended real number. There's no question of do they converge. They do, automatically. And that's the value of the series. You just take the limit of the partial sums. It's guaranteed to exist. Might be plus infinity. Maybe a real number. And that's the sum of the series. That's nice. For example, the usual convergent series of real numbers like sum from n equals 1 to infinity of 1 over n squared equals pi squared by 6. You may or may not remember. It's still valid. Still correct. Sum from n equals 1 to infinity of 1 over n, the harmonic series, is now infinity, as it was before, but it used to be a divergent series of real numbers. It's now, if you like, a convergent series of extended real numbers. Perhaps it's better to still think of it as a divergent series of extended real numbers whose sum is evaluated as plus infinity when you sum the series in the extended real numbers. That's a harmonic series. And of course, if any single term in the series is plus infinity, then you're stuck. It's plus infinity for good. Right? As soon as any of the xn's are plus infinity, you're bound to have some plus infinity. So it's really only interesting that these series are not very exciting if any of the terms you're adding are plus infinity, because you're bound to get plus infinity. The series are more interesting if you've got something like this harmonic series. Something like this harmonic series where you're adding real numbers, non-negative real numbers, and the result is plus infinity. Because, as I said, if any of the xn's are plus infinity, then as soon as you get to that term, your partial sum will hit plus infinity and it can never leave again. So that's it. Oh, right, examples. Well, I'll just give you some examples. I'll just finish those examples with the other thing I was going to say, that if any xn is infinity, I'll write plus infinity for once, just to remind you, then the sum from n equals 1 to infinity of xn. Well, let's call it xn naught here. If any xn naught is plus infinity, then sum from n equals 1 to infinity xn is plus infinity as well, since Sn naught is plus infinity already. And that brings us to the end of section 3.2. Do you have any questions about series in the extended real numbers?
I have a question about the multiplication.
Ah, yes.
How else would you define, like, you said there was a bit of confusion of 0 times infinity. How else could it be interpreted?
Well, have you ever thought that 1 over naught might be infinity? And that 1 over infinity might be naught? Maybe, maybe not. In some sense, one could. There is a sense in which 1 over infinity should be regarded as naught, but 1 over naught, and maybe 1 over naught should be regarded as plus or minus infinity. Some people feel that, some people might think that naught times infinity should be 1. And the reason you might have that, and it's going to come up again in the next section, is look at 1 over n times n is equal to 1 for all n. 1 over n tends to naught, and n tends to infinity. And you might hope you've got an algebra of limits. Don't make the mistake of thinking that it's true. No, the algebra of limits goes wrong in the extended real line. I'm sorry to say. We're going to see the algebra of limits and the problems with it. So the algebra of limits does not work here. We want naught times infinity to be naught, even though 1 over n times n is 1 for all n. And what that does is it doesn't say we've got our definition wrong. It tells us that there's a problem with the algebra of limits in the extended real numbers. If you want the associative law to hold, you see what you've got is you've got, let me try and turn that thing off, the toggle stopped working for some reason. Right, so let's have a look at 2 times naught times infinity. But let's bracket it that way around. We want 2 times naught times infinity. Okay, now we may not have decided what naught times infinity is, but we do know what we want 2 times naught to be. So this is for associativity. So you end up with twice naught times infinity. It has to be the same as whatever naught times infinity is. This leads to 2 plausible answers. But only 2. You could consider naught times infinity to be naught, which is what we're using, or you could try naught times infinity equals infinity. Anything else will violate this, because if you take naught times infinity equals 1, you're going to get twice it is equal to it, and you had it. But infinity is a plausible alternative, but then why should it be infinity and not minus infinity? Because what's the difference between naught and minus naught? So why should plus infinity win out compared to minus infinity? If you want some symmetry in the extended real line, then you better make it naught. So your problem wasn't this. Your problem was that what else could it be? I'm suggesting that some people might feel that it should be 1. And now I'm explaining why it can't be 1, if you want the associative law. You could say infinity should win, but that leads to problems later on. And so we'll have naught winning in the conventional system.
I just didn't understand, because obviously an infinity of naughts is always going to be naught.
That's true. So if you feel that that's what multiplying by infinity is, adding 0 together infinitely often, then you get naught. If you move to, well, I won't say that, that wouldn't be quite right. So the point is that your problem was not with what I said, but with why there might be a problem with what I said, okay? Which is a different style of problem. If it wasn't a problem for you, that's great, okay? But we will see next time about the problem with the algebra of limits, which is a bit of a nuisance, but we'll see how you get around it. Okay, so we'll stop there for today.